I think we can start.
Absolutely.
John or Ita, let me know when I can start.
Hi, Paula, I think you can go ahead. People are
Okay.
Go ahead.
Okay.
You can go ahead, Paula.
Okay, thank you. So hello, everyone. Welcome to the joint webinar between Impact and Valid projects. Thank you very much for joining us. I'm Paula, research scientist with Sintaf Energy Research and dissemination manager for the Impact project. I'll be guiding you through this webinar today. But before we move to the agenda, to our program, we would like to say a couple of words about the projects and also about the webinar. Valid and Impact projects answered the same call from the European Union Horizon 2020. The call was about new test rigs for helping to accelerate the development of wave energy technology. Both projects started in 2021 and have 3.5 years of duration. For more details on each specific project and the approach that we consider in these projects, you invite you to take a look at our websites, which you can see at the bottom of this slide. In this webinar today, each project will present a case study and how rig testing is contributing to the development of wave energy converters in the context of the projects. We also discuss the benefits of hybrid and accelerated testing, highlight challenges and key achievements from each project. So thank you very much for joining us. Here is the program for our webinar. We will have 1.5 hours. And the agenda for the webinar today is divided into 3 main sessions. We have 2 technical sessions dedicated to each project. These will last 25 minutes each, and 1 last session of 30 minutes with a panel discussion and questions and answers. The first session is dedicated to Valid project. The speakers, Ivan and Ada, will talk about WEC hybrid testing, lessons learned from Idon's case study. Then the second session is for Impact project, where Giacomo and Sam will discuss the experience from designing and executing tests on Carnegie Clean Energy's C2-6 belt. And the third session is for panel discussion, question and answers from the audience. Claudia from Valid Project will be moderating these discussions and the questions and answers. If you have questions for our speakers, please write them in the chat, and please indicate to whom you are addressing the question. Either write the name of the speaker or the project name that should be answered the question, or if the question is to everybody. And we'll try to answer all of them in the third session, but also if we have time after each one of these sessions, after the Valid session or the Impact session, we also give you the opportunity to ask your questions live. So just raise your hands. If we have time, you have the chance to ask them the questions yourself. So I think it's too much talk from my side. Thank you very much for your attention so far. It's time to start with our first technical session. That is the Valid session. In this session, we have Ivan Ruibal, that is engineer with IDOM, and Eider Robles, that is a research engineer with Tecnalia. Welcome, Ivan and Eider. You can please start sharing your screen. And just as a kind reminder, this session is 25 minutes. Please, the floor is yours. Thank you.
Thank you, Paula. Well, good afternoon to everybody. I will start with this part. My name is Eider Robles. I'm researcher at Tecnalia, and I'm working within the Valid project. The idea behind this project is that most lab testing has been focused on functional tests, merely proof of concept, performance, but there are other measures that usually are not taken into account in this stage, like reliability or survivability. And the reality is that performing component testing in real conditions in the lab is quite difficult, because we cannot reproduce this in the laboratory. We cannot reproduce the external environment and parameters like salinity, humidity, or things like that. Full-scale testing is very expensive. Monitoring is also quite difficult in laboratory, and also considering scaling effects, it's very difficult in the laboratory. So these are things that we are considering within the VALID project. So next, Ivan. What we want to do in the VALID project, it's the hybrid testing. And what is hybrid testing? We try to perform accelerated tests in the physical test rigs, but we are going to combine the knowledge from the real environment, where maybe other tests may have been performed, and also numerical models for those parts of what we want to test that are not physically available in the test rig. And they are accelerated tests because we want to induce the degradation on the component under test. We want to degrade it. We want to induce this degradation, the degradation it may have over its lifetime in the sea, but we have to do it very fast. So what we can understand of this degradation process, we can understand it. Maybe we are able to estimate the degradation in order to make some predictive maintenance, or even to be able to size it better. So this is our idea. And what we are going to consider in our user case is going to be the electric generator failure. We want to understand this failure, and we are going to do it on an OWC. We have two examples of OWC near. We have the Mujiku wave power plant, and this is an onshore OWC. And we also have the floating IDOMS Marmok, which has been also tested over 2.5 years in MIMEP in the sea. And so we have information from these two kinds of OWC. And we are going to use the test bench we have in Tecnalia for performing the tests.
Hello, everyone. My name is Ivan Ruibal. First of all, a brief introduction of who we are, IDOM. IDOM is an independent company focused on providing consulting, engineering, and architectural services. We are present in 125 countries and count with more than 4,000 professionals. The 95% of our billings are international, and despite being an international company, we are also dedicated to some niche markets, such as the wave energy. Moving to the technology that aimed the development of this project, the OWC technology, or oscillating water column, is a technology that employed in wave energy conversion. It harnesses the power of ocean waves to generate electricity. The basic concept involves capturing the rising and falling motion of water within a chamber, caused by the oscillation of waves. The earth chamber is opened at both ends and partially submerged in the water. As waves approach, water levels within the chamber rise and fall due to the wave motion, changing the water levels and creating air pressure variation inside the chamber. This pneumatic power derived from the pressure change between the air inside the chamber and outside creates an airflow that moves the turbines installed in the upper side of the chamber. This turbine spins an electric motor that transforms the mechanical power into electrical power. The oscillating water column technology is advantageous because it is relatively simple, robust, and can capture energy from a wide range of wave conditions. OWC systems are often implemented near coastlines or offshore to harness the continuous wave from ocean waves and contribute to renewable energy source. This technology was widely tested during the Opera project using the full-scale prototype Marmok 5 for 2.5 years, including 3 consecutive winters with waves up to around 14 meters. during the Borrasca Bella. And the Marmok implements the WEC technology offshore, which adds the dynamic of the device that enters in counterface with the waves, expanding the energy absorption. The most critical subsystem of this technology is the power takeoff, or PTO, which consists of the turbine and the electrical generator. This subsystem is highly compromised due to the nature of the technology, as the electrical machine is used far away from its nominal operating point with large dynamics. The Mochiku plant follows the same wave energy conversion technology as the Marmoka 5 prototype. However, it is an onshore application, which makes it more accessible for maintenance and monitoring. The backdrop is that it receives more attenuated waves than offshore and loses the relative movement of the chamber. Mochiku is a home to the first commercial wave energy plant in Europe, which has the longest lifespan and highest number of operational hours. As of today, it has generated a cumulative 3 gigawatts-hour of electricity. As mentioned before, the energy conversion from the sea waves to the electrical grid follows the scheme shown here, starting with the waves energy that is converted into pneumatic energy and then into mechanical energy by the turbine. And this movement is converted into electrical power through the induction generator. This generator is controlled by a closed loop in order to protect the device from excessive overloads and to maximize the power extraction. Following the major issues that we have experienced in the past and in accordance with the opinions of other developers in this field, the PTO subsystem is the most critical component in this technology. This is due to the need to include a generator that can absorb peaks with several times the mean power, which significantly contributes to the yearly power generation, without penalizing the overall efficiency too much during low power waves, which occur most part of the time. The stator winding is responsible of the 65% of all failures within the generator. Its main stress factors are thermal, electrical degradation, and external environment. While the external environment also plays a role, it is difficult to reproduce in a lab without specialized equipment such as climatic chambers, so it was skipped during this project. The two main important outputs from the work done in this project are the generator sizing, because big amount of the time the generator works far below its rate, but also great part of the time it will need to withstand with high power peaks. The second one is achieving a condition monitoring for preventive control methods in order to increase the reliability and decrease the out peaks.
Well, this is a complex slide. We have a lot of information, but it's just to say that we are going to use digital models, experimental models, and also information from the real environment. We are going to do the accelerated test on the test bench that is completely sensorized. Give two times, Ivan, please. And to be able to know which input we have to introduce to effectively accelerate this test, we have both. We have information from the OWC IDOM model, from the Marmok model, the behavior of the real model. And also we have information that IDOM gathered when the Marmok was on the sea. So as I said, we are going to perform the accelerated test. And how do we perform this accelerated test? But basically, we have two ways. We can increase the amplitude of the degrading factor, or we can increase the time. So we apply the degrading factor during more time than in reality, so that we can have the same, or we can try to have the same degradation that the device, the component, in this time, the electrical generator, will have over the life. So we are performing a big amount of tests of increasing power in order to be able to break the generator faster than in reality and to understand how this degradation is producing. for us, the degradation factor is the temperature. So if we want to do some preventive maintenance on the generator, we work on the following digital models we see there. And these models, we want to validate them with the test we are performing on the test bench. So we have an efficiency model that can give us the losses of the generator. We have a thermal model that with these losses can give us the temperature or the estimated temperature, which is the degrading factor for the electrical generator. And we have at last a degradation model that with this temperature will give us potentially the remaining useful life of the generator. So we can use this information for example, for changing the control strategy in order to smooth the behavior and reduce the temperature that is degrading our generator. So as a summary, we are doing some accelerated tests in the test bench. We are building these 3 models and validating them with the results we are obtaining in the test. And we are using as input information from IDOM, from the MARMOC. We also have Mutriku. Mutriku is also completely sensorized. At the beginning, we tried to perform in real time the test, having real information from the sensors of Mutriku, but it was not possible to do it in real time. So now we are trying to get use of this sensorized this information of Mutriku and make some comparisons to see if what we get in the laboratory is similar to what we can see in the process of Mutriku.
The dataset used to fill the test rig, the numerical models follows this structure. First, usable C states per nominal power are taken from raw data time series. Then, with the MARMOC model, as Either explained, the peaks are analyzed. The power time series statistic analysis are performed with the peaks distribution and repetition. The peaks characterization with histograms, peak power, wave shape, power, energy, duration, and the time distribution of peaks. And finally, the time series for test are defined.
Sorry, this is the graph of the test bench we have. So basically, we have two parts. It has an emulated part that it's going to be used with a numerical model that it's going to represent in the shaft of induction motor the same behavior that the device will have in the water. In this case, it's an WEC, but we can represent any other device that has a rotary movement. And it's composed by an induction motor and a power converter that drives this induction motor. And then we have the real part, which is composed by it's composed of an electrical induction generator, the one we want to do test on, and a power converter that is connected to the grid. And this part is representing the same part, the same components that will be on the water. Next. This is just a picture of our test bench. So on the right, you see the induction motor, the drive motor. It's much bigger than the generator you see on the left, because as we want to do this accelerated test and we want to impose high power peaks for this generator, we have changed the generator we had previously in the laboratory in order to be able to perform this high power test. We have the two power converters, one for each of the machines, electrical machines, and we have a lot of transducers, sensors. It's completely sensorized, the test bench. Next. This is just the table to show the test we have performed on the first generator. Within Valid, we have both 3 equal generators, and our idea was not sure if we are going to be able to do it, to test the 3 generators and to compare to see how they are degrading. And so on the first generator, we really didn't know how much time and what kind of test we needed to break it and to be able to see the degradation. So we started with low power test, and we went increasing this test. We performed 2 kinds of tests, nominal, a constant power test at different powers, and also variable power tests when we were using these power peaks, very high power peaks and very fast power peaks, not the same as in reality, that maybe in a sea state we made the generator will withstand some peaks. In this case, it's withstanding very fast peaks all the time. So these are you can see here the RMS power and the peaks we are subjecting the generator to. It goes from low power to high power. In yellow and in orange, you see the highest or the strongest test that completely break the generator in the end. So we think that the generator broke between these 26 and 27 tests. And as you see, we were in the 27, we were performing tests nearly in the double of the frequency, and it's not a peak of the double of the power. It's a constant RMS power during, for example, 5 hours. So it's they are very high power test. And here in the picture, you see the generator after it broke. So it was completely burned. Yes, and what we have done here is also to compute how much time the generator has been under different temperatures. In our case, our generator withstands a temperature of 155 degrees. This is the thermal limit of the generator, and it has a breaking limit of 220 degrees. So we have computed how much hours has been the generator in our test under constant test and in variable test in its temperature. Maybe it's easier to see it in the next graph. Ivan, yes. So here you see the amount of time that the generator has been below the thermal limit, above the thermal limit, but before the breaking limit, and the hours it has been above the breaking limit. It has withstand less hours above the breaking limit, around 16 hours before breaking. Yes. And this is the test plan we have for the second generator. We have started already with this test. We have started, in this case, as we know more or less how it has behaved the first one, we have started with harder test, directly with, first with constant power test and then with variable peak test. But in this case, we want to break it, to be able to break it in very few weeks. So we are performing harder test, and for the moment, it hasn't breaked. And well, regarding the models, the first one is the efficiency models. We are going to use it to compute the losses. It has been validated with the test, and you can see in the graph how the efficiency evolves with the capacity factor. This is not RMS, is the mean capacity factor, which is torque multiplied by the speed. In the test we performed in the test bench, for the facility of the test bench, we are using nominal speed, and we are varying the capacity factor of the torque. So the measure that meant that varies is the torque. And we see here that the best efficiency, more or less, it's given at 80% of this mean capacity factor. The losses increase with higher peaks, which is something that we may think that it's normal. And in this second graph, what we have done is to analyze and to segregate with the efficiency model the generator losses. And this is also a good piece of information, because we see that the main losses are the Cooper losses at the stator, which are in fact the ones that produce this temperature increase, that is our degradation factor. So we see that these Cooper losses in the stator are higher with higher capacity factors. It's a good information for us to understand how the temperature is increasing.
Regarding the thermal model, we are working on different approaches for it. The first order thermal model follows the equation shown here. As can be seen, it is a simple model that follows an exponential curve. The theta with series factor equal to 1, the nominal current, the sample time t, and heating time constant tau are considered constants. The theta ambient, instantaneous RMS current, and theta minus 1 are dynamic and changes at its sample time. On the right side of the slide, a comparison is shown between the response of the first-order thermal model and the temperature of the stator winding of a generator installed in the tree. The constants of the thermal model were obtained from this temperature time series, and the model was fit with the current measurements of the power electronics of this generator. As can be seen, this fit is quite accurate. In order to achieve a better thermal estimation with a more complex model, a second-order model has been developed. In this case, the model is based on two solids that conducts the temperature between them and with the ambient. In contrast with the previous case, where only one solid is considered. The two solids considered in this model correspond to the case and the stator winding of the generator under study. In this slide, can be seen the comparison between the first order and second order thermal model developed. It's true that the accuracy has increased, but not significantly. So the first order thermal model has been considered more cost effective. A drawback of using a simplified thermal model is that the constants obtained do not fit really the real temperature in all operating ranges due to the variation of material properties. These constants are not static and can be optimized for a specific temperature range. However, if a more accurate model is desired for all temperature ranges, the constant considered must be variable with the temperature. Additionally, thermal models based on obtaining the capacitances and conductances through differential equations have been developed. However, the results obtained were less accurate than those obtained using the two models mentioned here. Moving to the degradation model, the modified Arrhenius model has been developed and implemented in the test, trying to predict the failure movement based on the temperature of the winding. To have a better understanding of the stator winding insulation, these are typically categorized into 5 types listed in the IEC standard 60034, part 1, from class A to N, with increasing maximum allowable temperatures. The insulation of the generator under test is a class F with a maximum temperature of 155 degrees and an estimated life of 20K hours under operation at that temperature. The evolution of the remaining useful lifetime of the different classes versus the temperature can be seen in the graph in the right side of the slide. And the different maximum allowable temperatures by design of the classes are in the left side. Based on the rule of thumb that the remaining life of the insulation decreases at its half per each 10 degrees increase, and the modified Arrhenius model, a degradation model has been developed and behaves as shown in the left figure, where the blue line is an example of the temperature evolution of the stator winding during a test, and the orange line is the evolution of the remaining life having that temperature as input. The table presented in the right side corresponds to the IEQ STD 117, which presents the standard test procedure for evaluation of systems of insulating materials for electric machinery. And as can be shown, follows this rule of thumb of the 10 degrees. This graph comes from the experimental results in the test bench. It shows the final temperature after different kind of tests, considering the x-axis as the RMS power. Here are different plots. The blue line corresponds to constant power tests, and the orange, gray, and yellow correspond to with peaks of increasing amplitude. We have seen that the temperature increase depending on the RMS power, not on the amplitude of the peaks. That means that the degradation doesn't come from high capacity factors, comes from the temperature. We also notice that the breaking temperature doesn't arrive until higher torques than what we thought. In the right figure is also presented this data, but all gathered under the orange color. It also adds the comparison with the different temperature achieved in Montreal with different capacity factor in blue and electrical power in the bench computing the losses of the converter in gray color.
I'm going to be very fast because we are running out of time. Just to say that for condition monitoring, we have tested different methods. Most of them analyze the frequency components of the voltage or the current of the generator, and to see if these frequency components have changed, because different frequencies imply different degradation on different parts of the generator. But the reality shows us that it's not so easy and so straightforward to estimate this degradation. When have we, Ivan, next. When have we seen or detected the degradation on the insulation? The reality is that we have nearly detected it once it is already broken. We have not been able to estimate the degradation as gradually as we thought. Next. Because theoretically, the techniques we have in use, MCSA techniques, implies that if we analyze the frequencies of the current, we can see that some frequencies different to the fundamental are going to be triggered due to different failures. So if one of these frequencies starts to grow, we can deduce that this component or this part is degrading. But the reality is that we've seen that this winded failure does not evolve gradually. So it does not evolve gradually over time. The frequency that indicates the failure when making the FFT, it's going to appear once the failure has already happened. So we are not able to see that it's going to degrade with this gradually. So this is the conclusion we have. And we have speak to people that works on these kind of things, and they told us that this fault evolves not from 0 to 100, but nearly to 0 to 100, and we cannot see how it's evolving. So this is the conclusion on this estimation. The main challenges we have seen during the project for the moment is the difficulty to find the correlation between the instantaneous power peaks and the sea states that produce these power peaks. The real doubt if these high temperatures we are applying on the generator are going to be achieved in the sea. And also the certainty of when the generator is going to break. We have broken only one, but maybe we go to another generator and it's not going to behave the same way. Also, the thermal model, to obtain an accurate thermal model for the whole operation range is difficult. Scalability is also an uncertainty. And condition monitoring, as I say, difficulties in estimating this progressive degradation. Yes, that's it. Thank you very much. I'm sorry for the delay.
Thank you.
It's okay. Thank you very much, Ivan and Nader, for your presentations. I think we'll just move to the next session now and leave the questions for the panel session. So our second session is dedicated to impact project. We have Giacomo Alessandri, Senior R&D Engineer with VJ, and Sam Nilsson, Engineer with Carnegie Clean Energy. Welcome, Giacomo and Sam. You can please start sharing your screen.
Thank you very much, Paula, and welcome everybody to this second session, which is about the experience from design and execution of the test on the Carnegie C26 belt. This is the agenda of this session. So we'll have a brief introduction of the impact project and an overview of the Carnegie company and products. Then we'll pass on the description of the C26 belt and on how the impact methodology framework has been applied to this case study. After that, we will present an overview of the setup design and test execution, and finally on the results and the next steps. The impact project has been awarded within the Horizon 2020 framework and has two main objectives. The first objective is to design two novel test rigs that can allow to target testing of components and subsystems that have the major impact within the LCOE of a device. At the same time, we are also focusing on defining novel test criteria and metrics, which allows on one end to reduce the test time, and while on the other increasing the reliability of the device under test and ultimately of the overall wave energy converter technology. These objectives have been broken down into 5 different sub-objectives. So the first one is related to the drivetrain test rig, which is a test rig that is able to address the test of the conversion chain from input mechanical power up to the grid interface. This means that all the subsystems listed on the left of this slide can be tested within the drivetrain test rig. And the rig has been designed so that it can cater for both rotary generators with the respective actuator installed on the left side of the rig, or with linear actuators, linear generators, where you can see the actuator on the right side of the rig. The second test rig and the related objective is focusing on structural components. With structural components, we mean mechanical interfaces within a wave energy converter, mooring lines, dynamic power cables, and sealing systems. These are all components that are subject to loads and therefore can be tested in different arrangements within this rig. The rig is made up of a linear actuator on the left side, a central part where can be installed a submersible area by using a dedicated tank, and then on the far end of the rig you can see the test cell, which is a cell made and designed to host the device under test or part of that, and for which a dedicated test setup is designed for each type of test and each device under test. Both rigs have in common some features. First of all, both of them allow the characterization of the device under test. They also allow hardware-in-the-loop test to be carried out and accelerated test. There are, as I said before, 5 sub-objectives. The number 3 is related to the integration of the test rigs, the drivetrain, and the structural components within a platform that is able to run 2 tests simultaneously. So we can pass from a hardware-in-the-loop test to a dual hardware-in-the-loop test, where we can connect both devices under test to the same numerical model. As I said before, there is another objective that is addressing the development of novel methodologies and test-derived metrics. And the last sub-objective is the most important, because within the project we are demonstrating all the previous sub-objectives related to the rigs, the platform, and the novel methodologies and metrics to proof that they can have an impact on the development pathway of WEC technology. Now I'll pass the floor to Sam Nilsson with an introduction about Carnegie.
Hi, everyone. I'll just give you a quick brief overview of who Carnegie are. We're a wave energy developer based in Perth, Western Australia, with subsidiaries in Spain and Ireland. And we have a portfolio of products that we're developing at the moment at various stages, various TRLs. The two flagships of those are CETO, which is our main commercial scale wave energy converter, and More Power, which is a spin-off product for aquaculture. But additionally, we have a wave predictor, which allows you to predict the conditions at a point in a wave field ahead of time, which is useful for controllers and for conditions prediction, and also a mooring tensioner, which was developed for our CETO product and has applications elsewhere. On the next slide, I'll talk about More Power briefly. More Power is a spin-off, as I mentioned, of our main CETO device, where we take the power takeoff, the PTO, and put it onto a fixed floating structure. Typically, our target case for that in the short term is aquaculture vessels. And in Tasmania particularly, there are lots of aquaculture vessels which have a lot of onboard electricity generation required, but are currently relying on fossil fuels such as diesel generation. That, combined with the fact that these have some environmental concerns around soiling the protected bays with the waste products from fish, means that they're being pushed into further and further out to sea into areas with better flow. And the combination of this expensive and carbon-heavy diesel electricity generation and a more available wave resource has been the genesis of the More Power product, which is to start supplementing that diesel generation by using a modified power takeoff from CETO on those fixed platforms. At the moment, actually, in the last couple of weeks, we've deployed a scale demonstrator of that system off of our facility in North Fremantle in Western Australia. The picture here is just a little bit out of date because we do have it in the water where that arrow is pointing at the moment. And if you're interested in seeing a bit more about that, you can check our socials to see a bit more information. The main product that we're talking about today is CETO. So that's our commercial scale wave energy converter. It's a fully submerged device that sits a couple of meters under the water, and at full scale it's 20 meters across or around that size. And then we're also deploying a scale demonstrator of that as part of the phase 3 of Europe Wave at BMAP off of Arminsa in Spain. A little breakdown here on just how the unit works for those who aren't familiar. So the large green body at the top there is the buoyant actuator. Sits a couple of meters under the water, depending on the sea conditions. And it's the main conversion feature between wave energy and mechanical energy. So it's actuated by the waves and moves relative to the seabed. And our belt, which is our device under test in impact, forms the tether between that buoyant actuator and the seabed. I'll show you how that converts that linear motion of the BA to rotary motion is via our translation system. So the belt comes, the bottom part of that belt there is reaching out toward the seabed. It enters the BA over the self-aligning sheave and wraps around a drum inside the unit. That drum then rotates, which is connected to a generator, and the rotary motion from that is then used to generate electricity. We have another couple of components in the system. We have a tensioner, which I mentioned on the first slide, which is to provide the offset load such that the motor isn't constantly having to apply a torque to hold the unit under the water. And additionally, there's a self-aligning sheave here, which is what our test rig is consistent of, is a number of these sheaves. In the unit, they rectify misalignment between the belt and the drum. If we weren't to have a feature like that, the belt would be very misaligned with the drum and damage and break itself almost instantly. So as the belt enters the unit, it rolls over that self-aligning sheave, which can actuate about its pivot axis, ensuring that On the drum side, it is aligned and only experiences twist, and on the outside, on the C side of that self-aligning sheave, we only see a little bit of fleet due to the dynamics of that self-aligning sheave itself. So our belt is a repurposed we're utilizing an existing product which is currently used for power transmission. So it's a poly V belt, a tooth belt used similar to like a fan belt in your car, used to transmit power. It's about 470 mils wide. It's got a number of load carrying cores inside it, and they're what carry the tension. And then the teeth are a legacy feature which we don't really require. That's typically to do the power transmission role when it's being used as a poly V belt, but we use them to ensure that it stays on the sheave itself. And then we define what the conditions that we need to test this belt with are. We do that through a number of means. We have an in-house simulator that we can use to determine the motion of the unit, and we validated that against the tank in a number of tank testing campaigns. And so from the data obtained through those two methods, we can determine with additional simulation what we expect the misalignment to be, and start developing a test plan from there. We see a number of misalignment and CBOS, or cyclic bend over sheave, load concentrations. Cyclic bend over sheave is when you have the belt wrapping over that small self-aligning sheave. The bending cycles that the belt experiences damage the cords inside the belt, and that effect is magnified by a number of different parameters. The first is the tension on the line. So higher tension results in higher damage and a shorter lifespan. But additionally, misalignment in the form of fleet, which you can see in that middle image there, will result in higher cord tension, and so more damage. And we also have twists in our system. So on the far right, the combination loading that we expect is kind of highlighted there, showing how that CBOS damage, that cyclic bend over sheave damage, is concentrated.
Yeah, then from these aspects, we started to define the specificities of this test, and to do that, we applied the methodology framework that was developed within Impact. This framework can be applied to different subsystems and components such as PTO, interfaces, mooring lines, and dynamic power cables, which are basically the objects of the Impact test rigs. And this framework focuses on some key evaluation areas, specifically performance, reliability, and survivability. The framework is based on 3 different layers of building blocks. These building blocks start from the bottom, where we have the foundation block, which defines the stage of testing. The functional block, which is the middle one, defines the tasks that are associated to each stage of test. And the last one, the input block, defines the specificities that are required for each task. So now we are going through what has been the application of this framework to the C26 belt case study. Before we just have a look at of what are the main foundation and functional blocks. The foundation blocks divide the testing phase in 3 parts: the pre-processing, processing phase, and the post-processing phase. And as you can see from each of these phases, there are tasks that have to be accomplished before moving to the following one. An important aspect we want to underline is that this framework can be applied to different types of tests, but specifically with Impact, we are looking at using 2 testing approaches, so dual hardware-in-the-loop testing or hardware-in-the-loop testing, and accelerated tests. This case study we'll present today will feature accelerated testing. So we have started with the pre-processing stage to define the inputs that would be required for the test, and this include the test conditions. So you can see the first block, the functional block, that test condition require the definition of environmental condition and WEC status. So in this case, where we want to analyze the characteristics of the belt and its properties in terms of fatigue features, we have looked at normalcy states for which the WEC could be in power production, either or in normal condition or in survival conditions. In terms of the test setup, we have focused on an accelerating testing strategy, from which we have defined a series of load amplitudes and number of cycles that are respective of the BMAP test site. And we didn't have to apply any scaling assessment, since we are carrying out tests at full scale, or real-time machine, since we are not practicing a hardware-in-the-loop test in this context. Finally, for the rig setup, we have to identify what is required, the requirements in terms of hardware, and what is required in terms of preliminary test. So since we need to apply tension to the belt while cycling it, we will use a geared motor, which will apply the belt rotation, while we will use a tensioning system that can tension at different values the belt. And finally, we will check what are the motion while carrying out the preliminary test on this actuation axis. Once this was finished, we passed to the processing stage. So in the processing stage, we install the device under test and the transducers. In this case, the device under test is indeed the belt that will be wrapped around different shifts, and the acquisition system that will feature one linear and one rotary encoder, a test cell to measure the tension, and strain gauges to measure the deformations. Then the first test is what we have called as a functional block basic testing. So the basic testing will feature tests on the signal logging that have been done during the run-in of the belt, and the characterization of the DUT, that which in this case is mainly related to the correlation between load and strain. And after the basic testing, the phase of what is called advanced testing is, as I said before, the characterization of the fatigue capabilities of the belt. And in this case, we have defined a detailed test plan. I will show you in a couple of slides. And of course, during test, we would monitor load speed and the absorbed current by the motor. The last foundation block of the framework is the post-processing stage, within which we include activities for inspection, data quality, and data analysis and reporting. So the breakdown of these tasks includes the inspection of the DUT and of the rig during and after the test. So in this case, after the test, we here at our facility have carried out visual inspections. And regarding the data, we have checked if there were duplicates or missing data, and if there was the requirement for data filtering, which was not necessary in this case. And finally, on the analysis and reporting, we looked at metrics to define the theoretical fatigue curve associated to the device under test, and to quantify what are the uncertainties related to the test. And finally, of course, we ended up with a reporting phase by indicating the characteristics and the reliability features of the device. So the test plan we have agreed with Carnegie includes a preliminary tension testing on a smaller scale prototype that was carried out at the supplier's facilities, for which we were able to define the theoretical model of the belt. characteristics in terms of fatigue. And then we identified two different phases of test, what we have called the basic tests with the duty characterization. This included static testing of the belt, for which we were measuring with an array of 12 string gauges. You can see here in the left side picture how they were placed across the belt width and length. And we were looking at the deformation at a fixed load, varying also the flit and twist angles, and what was the creep effect, meaning from when you pass from an unloaded belt to a loaded belt and vice versa. Another characterization test we carried out is the tracking testing. So the key here was to understand if there was the capability for the belt of keep their tracks of the teeth in different conditions, and especially when there was a very low load and high speeds. And finally, the advanced testing was featuring an endurance test simulating the damage of the belt equivalent of 2 years deployment time. And the table you can see on the right side describes the different tests that are included in this endurance test plan. And as you can see, we have a certain value of tension that is applied by the tensioning system, the linear tensioning system, that is increasing for each setup, and the setup is defined by the combination between flit angle and twist angle. For each of these rows, there is an associated number of belt revolutions and an associated test duration that is the output of the calculation that Carnegie did on the application of this prototype at BMAP. So once we have defined all these details, we pass to the phase of defining how the setup of the test could have been done. This is because this is not a standard test for which also the belt manufacturers are not used to investigate this kind of characteristics. So together with Carnegie, we end up in this concept. So we were looking at one sheave on the right side from which we would apply tension, and a combination of 3 sheaves on the opposite side of the rig, which would allow to apply twist with the light blue sheaves, and by acting on the center sheave and through the vertical pivot axis, we could apply flit moving all of these 3 sheaves. From the concept, we pass to the project. You can see here on this picture on the left what are the sheaves in terms of arrangement and in terms of interfaces. So here we would have the tension applied of the sheave. This is for making a comparison, the equal of the mooring towards the seabed for the C26 belt. Then we pass from this side where we have applied twist flit. We pass across this sheave that works as the self-aligning sheave within the C26 belt in this section where we apply twist. And this cycle is made twice for each rotation around the belt loop, since we are using a closed loop belt. And you can see from the top here that from this side, we pass across the sheave, from which you can see that there is an angle for which we have a difference in terms of flit angle. On the right side pictures, you can see what was the preliminary design of the setup on the structural components test rig, with the tensioning sheave being inside the rig and connected to the linear actuation system, while the other 3 sheaves were connected through beams at the opposite and far end side of the rig. From this step, we pass to the detailed project, and then you can see here the linear tensioning system that was using a trapezoidal screw to apply the tension, while on the other side, the two sheaves at the top and bottom of the pivot axis were connected with 3 different push rods. These push rods allow to arrange, to position the sheave at a defined angle in a 3D space, while the center push rod, the number 4, allowed to apply the fleet angle that was required for the test in a way of moving, of rotating the overall group of sheaves around this vertical pivot axis. These are some pictures for the test rigs. On the left side, you can see the initial test we did to verify the functionalities of the linear tensioning system based on a trapezoidal screw. And on the center picture, you can see a view from the inside of the rig. And on the right side picture, there is a view from the outside of the rig on the section where we apply twist.
Giacomo, excuse me, can you wrap up because we are a bit ahead of?
There are 2 short videos. This is related to the characterization test where we were measuring the deformation with the 12 strain gauges, and here it's one of the dynamic tests. In this case, was to check if the belt was running out or not. In this case, not. And in the overall test, there was a good tracking capability. I'll pass to Sam regarding the results.
Yeah, I'll rush this through because we're a little bit over time. But essentially, we've done a number of tests, and we're trying to characterize the material properties of the belt. The first plot here is just showing the creep behavior, how it relaxes over time. This was a 14-hour test showing that the belt reduces in load. The second is the hysteresis behavior of the belt, so how efficiently it can operate, because obviously we're worried about not losing too much power through the belt itself, and also the efficiency of the belt in rolling over those sheaves. And then our next steps are to finish the endurance testing. We are partway through that, but it's quite a long campaign because there's quite a lot of cycles to test, after which we'll dissect and inspect the belt for damage in the fibers. And update our models to reflect the material properties that we've discovered in this test campaign.
Okay, just before jumping to the Q&A session, we wanted to say that there will going to be a workshop about rig testing at our facility, where also this test on the Carnegie C26 belt will be showcased together with a test on the drivetrain test rig. So if you are interested, I will write into the chat the link to the web page where you can check all the details, and registrations are already open. So if you are really interested into rig testing, we will check with this topic with different perspectives in different sessions in April in Italy. Thank you very much.
Thank you, Giacomo and San, for your presentations. Now we are moving to the panel discussion and question and answer session, which will be moderated by Claudia Sanz from Aquaterra and Valid Project. Please, Claudia, you can take the lead.
Thank you, Paola. Thank you, Ada, Ivan, Giacomo, and Sam for your presentations. And we will now begin the panel discussion and Q&A session. So if you have any questions, please start sharing them into the chat. Do you have any questions?
There is one question on the chat from Jonathan Colby.
Okay, I will read it out. So for both valid and impact presenters, were the suite of IEC TC 114 standards considered for your test campaigns? If yes, do you have any feedback on their applicability? If no, can you comment on why not? So would anybody like to take this question?
Giacomo, I believe you are speaking, but we cannot hear you, at least from my side. No, still the same problem. May I invite you to go to your micro and maybe select the speakers? It could have changed during the webinar.
If
Now you are
anybody
muted.
else, sorry. Go ahead, Rachel. If anybody else would like to take the question while Giacomo solves his mic issues, perhaps somebody from the Valid project. We still can't hear you.
Even in either if you would like to say a couple of words about Valid while
Yeah, the only thing I can say is that we are testing, we are not testing the complete device, we are just testing a component, and for the moment we are not considering information from this standard. We have been considering the standards related to electrical generator testing, but not this TC 114.
Thank you, Ava. I think, Giacomo, we still can't hear you. So we can move on to the next
In that-
question.
Yeah, I would say in the case Giacomo is not able to solve the audio problem, we invite you maybe to write your reply on the question and answers chat. And in the meantime, there is another question, right, Claudia? From Claudio Ferreira.
I'll go ahead and read it out. So for Valid, can you have any initial thoughts on the degradation, higher or lower, for a generator performing oscillating movements instead of turning in one direction all the time?
Yeah, I can answer that. At the beginning, we thought that the degradation was going to be higher when we talk about because we have high peaks. But if we consider that the degradation comes only from the high temperature, what we've seen in the test is we obtain the same temperature for the same RMS power, despite or independently of the peaks we have. There was a graph on our presentation that shows that the curves that compare temperature versus RMS power go to the same temperature independently of the power peaks. So if we consider that the degradation comes from the temperature, we can say that it's the same.
Thank you very much, Eva. Ivan, if you'd like to add anything.
No, I agree with Eder about the oscillation. We haven't seen any difference with both direction or only just one direction in the degradation. So it's more related with the temperature of the generator instead of the directions.
Thank you, Ivan. Are there any other questions from the audience? If not, our presenters have prepared some questions in case anybody was curious. If at any point you have any further questions, please just pop it into the Q&A. So our first question is for Ava. So the question is, what other kind of tests are possible in the test bench you have in Technalia?
Well, As I have shown, the test bench has two parts, but the emulated part has a rotary generator motor, so we can emulate the behavior of any device that has a rotary movement. It doesn't matter if it is a wave energy converter, tidal energy converter, or a wind turbine. In fact, the test bench was part of Marinette 2 European project. And up to now, most of the users that have come to use the test bench, because we use it for our own research, but we have it also for the researchers, external researchers that come to Technalia. Up to now, most of the tests have been more regarding performance of proof of concept or control laws, especially control laws, to test different control laws, compare different control laws, or also to test the electrical behavior of something that they can change the generator and test the electrical behavior. So this is mostly what we have done. We haven't done up to now. Up to valid, we haven't done anything regarding reliability. It's the first time.
Thank you very much, Edith. I can see there's still no questions, so we will move on to the next question we had prepared for Ivan. So the question is, what is the maximum overpower the generators of Marmok and Mudriku have been subjected to?
In case of the Marmok, well, in both Marmok and Mudriku, the generators are limited to a specific power. In case of the Marmok, this limit was 3 times the rated power of the generator, achieving the square root of 3 in speed and the square root of 3 in torque. So in the maximum peak was 3. This limitation came from the supplier of the generator. It was their advice. And in case of in Motrico is quite conservative. So the maximum peak is around 1.2 times the rated power, maximum power of the generator. So there are those both scopes.
I can add, but in the case of Mutriku, this conservative part that is saying Ivan is because it is limited to this power. But we have seen that the generator manufacturer gives us the information that it can withstand at least 4 times the maximum torque. So one thing that we were thinking is trying that what happens if we don't limit the Mutriku generator to such a low torque. Maybe we can, Mutiku is able to extract much more power, and this is something that would be nice to test.
Great, thank you very much. Oh, we've got a question in the chat. I'll go ahead and read it out. So this question is for impact from Pablo Ruiz Minguela. Is the methodology framework described in further detail in a public document? Do you think the methodology would be applicable to other wave energy test benches? And feel free to take the question, Sam or Giacomo. I'm afraid we still can't hear you, Giacomo. Sorry.
That's all right. I can have a go at that one. No, yeah. In short, no. But yes, I think the methodology would be applicable. It is a reasonably standard miners rule approximation of fatigue damage that we're using in parallel with a physical model of the belt that we're using. But yeah, unfortunately, that's not in a publicly available document, and I'd have to look into what sharing requirements would be on further details on that.
If Giacomo, if you'd like to write your question, your answer to the question, please go ahead. In the meantime, we can maybe move on to another question. Thank you, Sam. So the next question is for Giacomo. So I'll read it out, and if Giacomo would be so kind to write out the answer in the chat. And then once that's done, we'll go back to it, but then we'll go out to the next question. So the question for Giacomo is, were other concepts evaluated for the combined application of cyclic bending, tension, fleet, and twist? So please, if you write the answer.
Maybe I can answer that one as well if
Okay.
Giacomo's having technical issues. And yeah, we did. The gold standard would have been a full PTO model that was of the same kind of arrangement as is seen in the WEC, which would be a model drum, a sheave as we had in our slides, going down to a load. It's a bit hard to embody a system like that on a test bench because you need so many different things to apply load to, and you need a lot of different actuators. So going to the closed belt solution that we did simplified a lot of things in that case. And we will actually do some of that arrangement when we do back-to-back testing of our PTOs after we assemble them. There were a few concepts that we considered in the early stages before landing on the one that we did, but none of them replicated the load concentration mechanisms I talked about quite as well as the arrangement that we ended up with.
Great.
And Giacomo, feel free to add more to that in the text part if you like.
Yeah, exactly. Thank you, Sam. We'll move on to the last question then, which is for yourself, Sam. So the question is, the tested belt is a closed loop while the translation system has an open belt. How can you correlate test data?
Yes, I touched on this a second ago. The system that we're using is a closed loop of belt. And it shouldn't really be thought of as the whole section of belt that you might see in the unit. We're actually testing every section along the belt as rigorously as the worst section of belt in the real application sees. By standard, we have one section somewhere along the belt that sees more cyclic bending cycles than any other over its lifetime, which is, of course, where we expect the failure to occur. And so to be conservative in our methodology, we test the entire belt as that worst section, which not only gives us a lot. It's still a single test sample, but that test sample is you can look at different sections of the belt and see if they aged at the same rate. And so that gives us some surety and a bit more confidence in the product that as Giacomo mentioned, is not typically deployed in the way that we deployed in.
Great, well, thank you very much. That is all the questions we had prepared. I've not seen any new questions appear in the chat in the Q&A section. So maybe we can give it a minute or so, and if there's no other questions, we can probably conclude the webinar. I'll pass it on to you, Paula, just for the last bit. Thank you very much, everybody.
Yes, thank you very much, Claudia, for moderating the session and also for the questions sent by the participants. I think then we can just move on. We reached the end of this webinar today. So I'll just share my screen. I have only 2 slides left. If you give me a minute. Yep, there I am. So if you have further questions that were not answered today, or if you come up with something after this webinar, please contact us. You can contact myself on behalf of Impact, or you can contact Natalia on behalf of Valid Project. Also, please remember to visit our websites and make sure to subscribe to our newsletters to learn more about our next events, activities, and also our results. And join us on LinkedIn. You can find a link to our LinkedIn pages in the main websites. Just go there and you'll find it very easily. So we'd like to thank everybody that joined us from their offices, from their homes, or from their home offices. Also thank all of the speakers for the presentations and availability to be here today. And finally, we would like to thank Trust IT Services, Rita and John, that helped us to organize this joint webinar through the Horizon Results Booster. So thank you all for being here, and thank you all for your participation. So hope to see you next time. That's
Thank
all
you.
from my side now.
Thank you.